Good afternoon, ladies and gentlemen. I just want to highlight a few things before I start this presentation. The title is a little bit ambitious because it says development of a bio-monitoring strategy, which is actually what we intend to do. But that is what we have not achieved so far. But I want to say that we do have results that shows that we are on the right path towards achieving that. This study was started as a result of the incessant pollution that has been happening in small rivers in South Africa. The big rivers are quite known for influx of materials from agricultural lands. But recently, small rivers like this one, the Swartspruit River, has been shown to have a lot of pollution downstream. Upstream is still quite good, but downstream has been so bad. The Atagana River in KwaZulu-Natal has seen a lot of pollution downward from Pietermaritzburg towards Durban. But upstream towards Mooi River axis, Mooi River is the name of a town, not a river. Towards the axis of Mooi River, the Atagana water has been very, very clean. So as a result of that, this study was started to look at Swartspruit River, which downstream running towards the Johannesburg axis has been shown to be very strongly polluted. Well, let me start by saying that these colleagues of mine, Emanuela Nablo and Rashid Adeleke, all work together. We are all parties at the University of South Africa, but we work from different centers. Rashid Adeleke works from the Agricultural Research Council laboratories in Pretoria, and Emanuela works from the labs in a place called Florida. It's not actually in the United States, it's very close to Johannesburg. And I work from the Pretoria Center. So what we tried to do was to look at the nutrient status of the river as a way of identifying the agricultural pollution that comes into the river and the exact concentrations that we are going to be seeing. This is because downstream in this river, the Swartspruit River, there's been some kind of algal bloom which people have believed came into as a result of agricultural nitrates and phosphates coming into the stream. And it's difficult to trace which farm exactly on the bank of the river is contributing most towards this. So we now started looking at a way of using biological entities to monitor the volume or the level of nutrients that comes into the river and at which point it comes in. So we now started from the upstream of the river to take samples and analyze the water and for the nutrients, and also culture the diatoms that we found in the freshwater upstream. The essence is to identify which diatoms were present in the relatively unpolluted water and which diatoms were present in the polluted downstream water. It was a huge task, so we decided to do it the laboratory way. We took samples of water from downstream and upstream, compared the phosphate and nitrate levels, and then decided to mimic what we found in the laboratory to be able to develop the indicators that we intend to work with. Basically, I just put this to show the sources and the probable consequences of the kind of nutrients that comes into the stream and what it could result in. So the nitrate and phosphates that enters fresh water, typical fresh water like the Swartspit River, actually comes from organic and inorganic sources, organic fertilizers and inorganic fertilizers, animal waste, and a host of such sources. However, some industrial materials do come into the system as well. So this will result in the whole chain, the increase in nutrient content causing growth of plants and algae, and then resulting in algae death and consequent activities of bacteria that will eventually result in huge respiration and consequently depletion of oxygen and the whole chain leading to eutrophication and so on. While phosphate is a limiting factor in the water system, nitrate may not necessarily be, or phosphate is in limited supply in the water system. The nitrate may not necessarily be limited. However, excess levels of both will result in high concentrations of nutrients in the water, which will result in algal bloom and the consequence of what we have just looked at now. Let me not labor us with these so much, but let's look at the results directly. These are the components of it. Now, in culturing the diatoms that we got from the river, these were the concentrations we tried to mimic. We'll have a range of phosphates from 0.003 up until 0.04. Normally, phosphates are required in very small quantities in the aquatic medium. However, the moment the concentration begins to increase, it begins to affect the system. With the nitrates, we have the nitrates from 0.1 to as much as 19 milligrams per liter. The characterization of the diatoms we took out of the river was done both through microscopy, light microscopy, and we later did a molecular work on molecular identification of the organisms as well. And that is just finished. And I'm not presenting the results of the molecular characterization here, but it's quite similar to what we found in this one. So I want to look at the diversity of organisms that we found, which is the interesting part of the study. We found that if looking at the control experiment, which comes from a mimicry of the water samples we collected upstream, we found these organisms in these levels. This organism, this diatom, was the highest we found in that series, followed by this, which is 23, and then a host of others of importance. We decided to consider those that are above 10 in count as important, and we found that these ones, which incidentally happens to be organisms we will find in the other cultures that we're going to look at, were relatively insignificant in their numbers in the control experiment. However, looking at the phosphate cultures that we developed, we could find that this organism, this same organism we found in the earlier culture, was dominant throughout, from the low concentrations of phosphate, which is quite low, to the highest concentration of phosphate. It showed a consistency in its concentration. But this other one, you'll find that it's quite consistent, but it's at very low levels. And this is another one that came out reasonably high. And then here, again, this organism that was very insignificant in the other one turned out to be quite prominent in this situation. However, if you look at the prevalence, it's almost the same thing across. So there's really no difference in its occurrence in all the cultures. I would want to highlight the occurrence of this organism. If we look at the low phosphate concentration, we see that it's quite high here, and then it becomes relatively low in the higher concentrations. And then looking at this one, the concentration, the counts are rather low. However, you'll find that towards the higher concentrations of P10, P11, and P12, it's almost zero actually. And then here is an inconsistent one. This is one of the organisms we thought could not be used for any biomonitoring activity because it's present at all times. However, the effect of the low concentration and the high concentration is rather confusing because they're about at the same level. Another organism to be highlighted is this. This is a very popular diatom in the freshwater ecosystem, and we find that it's just consistent across. Although much higher here, at the low concentration, you will find that at this concentration is still relatively high. There are quite a number of them that we picked up, four of the different species of the same genus, and they are relatively good, except the lowest one. There's nothing too unique about these ones. And then looking at the abundance level at the bottom, it just seems to be no significant difference. Now, if we look at the nitrate groups, we find this organism which we didn't find in the control. We find that this organism popped up and at the top was quite prominent. This other one, which also we did not find, popped up and was quite prominent. I found this, which one? That's the same thing like this, but another variety altogether. This one we did not find earlier and became relatively prominent. Here again is another species of navicula which has popped up again, and another one, and another one. And their counts have been very high in the nitrate cultures. The other organisms of importance is this, which we will look at the impacts later, and also this. This one we didn't find in any of the earlier cultures, but it popped up in the nitrate culture and was quite prominent as well. So looking at all this, looking at these organisms, it's an array of a whole lot of diatoms that were picked up. It was expected because it was a freshwater ecosystem, and that part of the river, the upper part of the river, is not really polluted. The cultures we use for inoculating comes from the upper part of the river. And these diatoms present that we identified were found out during the course of our culture management in the laboratory, that quite a number of them, which were present in the control experiment, disappeared completely from the other cultures that we made, the phosphate and the nitrate cultures that we made. Now we cascaded the concentration of the phosphate and the nitrate cultures until it got to a point where we thought that would be the highest, and we found out that there was a kind of shift from what we saw in the beginning and at the lower concentration to the top. Now the question is this. It's not looking at so many diatoms, which one you find here or there. But we started off by trying to develop a strategy to say that there is nitrate pollution here or phosphate pollution here. And we were a bit ambitious, hoping to find one or two or three organisms that we could use as indicators to say, if you don't find this, it means this water is polluted to this level with either phosphate or nitrate. But it didn't happen. Now the reason why it didn't happen is this, or at least what we think. The reason is because there is a constant shift in the community of diatoms that exist in the water. You are either finding the diatoms surviving up to a point and giving up, and another regime of diatoms comes into the system. That's exactly what we found. So are we now going to say that this regime of diatoms that we found in the beginning is the one that we are going to use to identify that this river is not polluted in terms of the nutrient concentration? Or are we going to say the other ones? Because if you saw what we saw just now, there was a mix of them, different varieties, but a mix of the same group of cultures, changing over the period. So we decided to use this technique to analyze what has happened. And there is clearly a separation of the group of diatoms according to the concentration of the phosphates in this particular case. There is a shift. Two minutes. There is a shift of these diatoms, this group of diatoms, showing up at very low concentrations, and this other group of diatoms showing up at the higher concentrations. So there is the negative and the positive drift of the group of diatoms that we have seen. And if we look at the nitrate one, it's almost the same shift. However, if you look at the nitrate very closely, you will find that it's almost difficult to say this group of organisms can be used for identification or not. But I want to say that this organism seem to have thrived, all the varieties of this one seem to have thrived well in the oligotrophic and the mesotrophic cultures. However, we have picked them up at the eutrophic cultures as well, but at very low levels. This other one, which I said we should mark at the point in time, is the one that has come to be prominent at, which has disappeared completely from the oligotrophic cultures. And there is this group, which we have picked up that are more prominent amongst the oligotrophic cultures. So we are saying that it is easy, or it is more feasible to look at this collection of organisms that we found in the oligotrophic cultures, which is the control experiment, as the standard for measuring, for looking at the relatively non-polluted water. And then this group, which disappeared completely from the oligotrophic group. So this group that disappeared, and then the species that were relatively abundant in the mesotrophic cultures, which we have identified, and those that depleted were completely depleted in the mesotrophic culture, and also the organisms which we have picked up to be dominant in the eutrophic cultures. These are the ones we believe could be used in developing further the biomonitoring strategy which we are trying to develop. So of the myriad of organisms that we have identified, there were those that were abundant at each phase of our study based on our grouping of the oligotrophic, the mesotrophic, and the eutrophic levels of contamination. This is one stretch of the Swastika.
Okay, so one final slide, please.
Yeah, this is the final one.
Great.
This is one stretch of the Swastika River that is really very contaminated downstream. However, the upstream part is still very good. So I just want to acknowledge these institutions that assisted in this study. And I say thank you for listening. In my language, we say Ngiyabonga kakhulu, which means thank you very much.